Right, let's begin. Welcome to Nachts auf der Sternwarte after the summer break. The weather looks fine right now, but the next clouds are coming, so we won't be able to see anything later on, but we will have a refracted tour after the talk for those who are interested. But first, the main attraction, Mr. Cameron Swiggum, Dr. Cameron Swiggum, I should say. Cameron finished his PhD exactly 2 weeks ago, successfully, in the group of João Alves. And that means that he has a good story to tell on star formation in the galaxy, moving nurseries, and I'm looking forward to that.
Great, thank you. Oh, free applause. Well, thank you all for being here. It's great to be here to tell you about work that I've been doing along with members of my group here in Vienna, and work that's been done with worldwide international collaboration, and to be able to show you a lot of these really cool results that have come out of here and many other institutes. So I want to start with an image. You might have seen this. This is an image that came out last week from the James Webb Space Telescope. And so what you're seeing here is a star cluster, a very young star cluster. And when I say young, I mean somewhere around 2 to 3 million years old. And this cluster was targeted. And so this cluster formed in a greater nursery, a greater stellar nursery. And you can see this nursery surrounding it, still forming stars here. And so one goal of that astronomers have is to really figure out what is this process of star formation. How do we go from something like this, which you see here, these dense gas and dust clouds, to a star cluster? And the issue is that star formation is a process that takes place over very long time scales. So to go from something like this to a star cluster takes something around the order of millions of years, and we don't live that long. So we have a static picture of star formation when we look at these regions. Now, to help illustrate what star formation might look like, I have a simulation here. So this is our best educational guess of what star formation in a nursery could look like over the time span of 5 million years. So when I play this here, every second that passes in this video is going to be something along the lines of like tens of thousands of years are passing every second in this video. So I'll play it, or not. There we go. Okay, so what you see here is a cloud. This is a cloud of gas, and you see all the structure forming here. You see this filamentary-like structure, very, very complicated looking. We call this turbulence, this structure. And eventually what you'll see happening is you'll see these white spots pop up. So these are stars that are forming within this nursery. So you can see some here. You see some forming here in these fibers. And so you don't need to understand everything that's going on in this video. The main point of showing this simulation here is to just show you how crazy a process like star formation is. So there's lots of things that are going on across many ranges and scales, across time scales of 5 to 10 million years. And what you'll see eventually is after the stars start to form, the very massive ones, you can see it kind of in the bottom left here, start to drive out these jets, these linear outflows that start to push the gas around. So not only is the gas going into forming the stars are misbehaving and pushing the rest of the gas outwards. And so this really starts to pick up. This is probably after maybe a couple million years. Now you start to see some star clusters. So you see regions where there's many massive stars. Now you see these bubbles here. These are tracing winds that are being driven by the radiation from the stars. And then also there are stars that are actually exploding within this region here. So again, as I said, this is a very, very complex process, and it highlights the difficulty of what we're trying to do by just looking at static pictures, right? This is a simulation, so this is just a kind of a best guess of what this looks like, but we really want to know what reality is when we look at these different star forming regions. And so I'm just going to speed this up here a bit so we get to the end, and you'll see at the end, what you're left with is this greater star complex, star cluster, multiple star clusters. And then all of that mess it was making, that the massive stars were making, pushed the rest of the gas out, and you're left with a complex, as it's the simulation is called Star Forge, so it has a Star Wars theme to it. You're left with a revealed star cluster here. So not only do we want to turn this static picture of star formation into a dynamic picture, we also want to know how the broader scales are at play here. So on the right here, I'm showing an artist's rendition of our own galaxy. So I'm going to be showing this actually a lot throughout this presentation. And what I want you to always remember is that this is fake. This is to show you a sense of scale. It would be great if we actually had this image, but we don't. But so this is a kind of maybe a decent guess of what our galaxy might look like. But what I'm trying to show here is that this complex that JWST looked at last week is part of a very, very small region. It's a very, very small complex, stellar nursery. And you can see the galaxy is full of these. And the galaxy, of course, is a dynamic thing. You know, we on Earth are going around the galaxy once every 200 million years. All the other stars are going around the galaxy, and the gas is also orbiting around the galaxy. And we want to know what effect does this have on star formation? How does the broader galactic scales affect this process? How do they help form stellar nurseries? Okay, so here's another simulation of a galaxy's gas, and this I'll play here. This is tracing timescales of 1 to 200 million years. So this is a galaxy that's rotating and it's tracing its gas around. So again, these are huge features that you see here. And then if you were to zoom in at any moment, if I were to pause it, you could zoom in, and then that region would maybe represent one of these very individual star-forming nurseries. So lots of physics is at play in this picture. And then another animation here, I like this one because it really highlights the spiral arms that you typically see in external star-forming galaxies. And I'll be talking more about spiral arms later, but you can see how the gas follows the spiral arms and passes through and out of them. Sure. So you mean, is this a process like, yeah, this is starting in some sort of equilibrium state. So yeah, the actual formation that goes into the galaxy isn't being modeled in the simulation here. It's just starting with one galaxy, at least for the time scales that I'm starting it at. You can actually see here that I'm starting at this animation starts at 500 million years. So it could be that the simulation has all of the things that might go into maybe the formation of the galaxy beforehand. That's a great question. This depends on a lot of different things. There are a lot of things that can do this. So this no more star formation that you're talking about, we call it quenching, and this can happen. For example, if the black hole at the center of the galaxy starts to become active, and that can drive feedback out and halt star formation. There's other galaxies. There could be another galaxy that's orbiting this one, and then they eventually merge, and this can have an effect on star formation. So many things that could be going on, but I think this simulation here might just be just one galaxy that's maybe isolated or something like that. But no, very nice question. Okay, so that kind of brings me to the two main goals of this talk from here on out. One is to turn the static picture of star formation that we have into something that's more dynamic, to try to actually trace the past histories of stellar nurseries in our galaxy. And I'm going to argue to you in a second that the galaxy is the best place. Our own Milky Way is the best place to do this. And so it's actually hard to fathom why this is the case when you consider our actual vantage point in the galaxy. So we're unfortunately stuck in our own Milky Way. We don't have this top-down view of the Milky Way that I was showing from this artist rendition. So that what that means is it's really hard to figure out what the broader scale structure of our own galaxy actually is. We're embedded within it, so we see it kind of from this edge-on view. There are many, many examples of face-on external galaxies, so galaxies outside of our own, where we do get this broader scale picture, where you can see, so this is an image, a real galaxy here, observed by JWST, and you can really nicely see the spiral arm features and the gas that traces it, and individual star-forming complexes here. So it begs the question, why do we care about studying our own galaxy besides the fact that it is our own? And why is our galaxy so useful for studying star formation? So to make a comparison here, so I've just selected a random region on this galaxy here, a star forming complex or a stellar nursery that's in this box here. And so we zoom in on it, and it looks like we have fairly decent resolution of it. We can see some individual features here, some different gas structures. There are different colors that might be telling you something different about different regions in this nursery. But it is going up against our view of nurseries in the Milky Way. And so this is a stellar nursery within our own galaxy that's about the same size as the one that I was showing in the other galaxy before. And you can see we have much better, much higher resolution data to be able to look at this in great detail. And of course, this isn't even close to the limit that we can look at this. This here is another JWST image. You might even recognize this. This is the famous Pillars of Creation, so a site of active star formation within these what are called pillars here. Okay, so to make sort of an analogy to our view of star formation in our own Milky Way and star formation in other galaxies, or at least our view of it, star formation in our own galaxy is kind of like being on Maria Hilferstrasse, where you can actually be on the street, see all the details, see all the restaurants, smell all the smells, get handed pamphlets that you don't want. Whereas our view of external galaxies is more like Google Maps, where you don't have maybe access to the fine details that you would have being in real life on the street, but you can see this broader scale structure. But we're trying to push to this broader scale structure within our own galaxy. So this hat sombrero looking thing here is called the Gaia Space Telescope. It was launched a little over 10 years ago by the European Space Agency. And what Gaia does is it maps very precisely the distances to stars within our own Milky Way. So it provides very, very precise distance estimates to over 1 billion stars in our own galaxy, which is crazy. And so if I'm going to show you now what this kind of looks like, what the real data looks like overlaid on this fake image, what we have access to now within, thanks to Gaia, within this relatively large region around the sun is a map of where stars are. So this might look kind of confusing at first. So these blue colors here, so again, this is the location of us, this is the sun. You can ignore the red points. The blue color map, the black to blue, where there's blue to white, this is regions where there's lots of stars, and the black is showing where there's not so many stars. So it's basically sort of a heat map of where the spiral arms are within our galaxy, because you can see they trace sort of these 3 spiral structures. So that's what we have now thanks to Gaia, and this map can even extend further out. I'm just showing the region that is probably covered by the best data. But we have something even, what I would say is even crazier thanks to Gaia. we have maps, 3D maps of interstellar dust within our own galaxy. So this, again, this is the same external galaxy that I was showing you before, and I've circled a region in particular because I'm going to compare this scale to something that I'm going to show you in a few slides here. So I'm going to isolate this and zoom in. So this, again, this is a patch of an external galaxy on the right here. On the left, what you're seeing is a reconstruction based off of Gaia data, stellar data, of the distribution of gas in stellar nurseries within a few thousand light years of the sun. So this, as I'll explain in a moment, this is built from stellar data, this huge catalog from Gaia, and it's, as I mentioned, a three-dimensional map. So we can do something really crazy with this map that we can't do with the map on the right here, is we can view it from any direction we want to. So it's this very broad, it's a three-dimensional map, and we can zoom in on individual star-forming regions and see them with really, really great detail, or we can stay zoomed out and kind of look at this larger structure here. I'll let this play a little bit here, maybe. So here, there's where you see the brighter regions. These are regions of denser gas and dust. So these are regions where there's likely star formation happening. And then you can also see regions that are above and below the plane of the Milky Way, where it's more diffuse dust. So this has been a really, really huge development for star formation studies within our own Milky Way, these 3D maps. So how do you go from stellar data sets to a 3D gas data sets? And I just want to know, does anybody know what this is here? I'm always curious to see if people know. Has anybody seen this image before? Yeah, and somebody want to shout out what it is? Good guess? That's a common one. It's dust. Yes, this is an interstellar dust cloud. So it's common, you'll see this a lot of the times on social media. Lots of people think this is a void, a very vast void. You'll see things, there was even something a couple weeks ago where they were reporting on this galactic galaxy void where there was no galaxies, and they showed this image. But this is actually an image of where there's a lot of stuff. So this is, as you said, this is a molecular gas cloud. This is full of dust and gas. This is a site of active star formation. And so because it's so densely packed with this gas and dust, there is starlight behind this thing that's not reaching us. It's getting blocked out because this is just so dense. And so if you go to different wavelengths of light, so this dust actually, it blocks out more easily bluer wavelengths of light than it does redder. So if you have an instrument that can look at further into the red part of the optical spectrum, you start to be able to see the stars that are actually behind this here. So you can see now, so there's nothing here. When you move to these further reddish wavelengths, you can start to map out the stars that are actually behind it and realize that it's not actually a void. So here's a cartoon kind of showing this, how this works here. So you have one star and there's this dusty medium in between it. And when the light of the star passes through here, it gets a little bit dimmer and the star gets a little bit redder. So this effect, you can see it. And then when you do this for a bunch of stars, this continues to happen throughout the cloud. And what you can do then is, if you know the locations, the distances of these stars, what you can do is you can map out how much dust is in between us and how much dust is in between the star. So if you know where these stars are, you can reconstruct what the cloud in between yourself and the stars actually looks like. And then there's a lot of other complicated computational stuff going on to get these maps, of course, but that's the basic principle here. So this is showing this, again, this top-down view of this three-dimensional gas map or dust map that we have here. It's not quite covering maybe as much as you want, but it is a relatively large patch of our galaxy where we're actually starting to possibly probe some spiral structure within this map. Yeah. It's measured via parallax. So yeah, so they're all parallax measurements. So parallax, if you know parallax, or if you don't know parallax, what it basically is if you stick the common way of demonstrating it is you stick your thumb out right in front of you, you block one eye, and then so I'm choosing you right back there, and then I cover your face with my thumb, and then I switch the eyes that I'm viewing, and then all of a sudden I can see you, right? Because there's a shift between where my eye is on this side and this side, so I can see this relative difference. And then so if you're closer to me, or if my thumb is closer to me, the shift gets bigger. That's the same thing we're doing with stars here. We're seeing the shift as the Earth goes around the sun. Then when it's on one side of its orbit, it sees the star in one part of the sky, and then when it goes all the way to the other side of its orbit, the star has shifted on the sky, and the shifts can be translated into a distance because this depends on how far away the star is. Is Gaia orbiting, or is it at a? Yeah, it's orbiting along with this. Yeah, it's in a stationary around the sun. I can't remember exactly where it is in its orbit. Yeah. So one of the features that's popped out of these 3D dust maps that have come about in the past couple of years is called the Radcliffe wave. So this is a structure that was discovered by my advisor, or my former PhD advisor, João Alves, professor here at the University of Vienna. And so what this feature is again, this is again a bird's eye view of one of these dust maps. This region didn't have any data, so that's why it's blank here. But this region, what they found was that when you look at the distances or the distributions of all the very dense star-forming regions within this region of our patch of the galaxy, what you find is a good fraction of them are located along this linear feature here. So they called this the Radcliffe wave. So it's a 10,000 light-year long gas feature. And the reason that they deem it to be a wave is when you take this picture, and instead of looking at it with a face-on view, you turn it to the side and you look on the side-on view, you can see that it has this undulating structure up and down, bobbing up and down in the plane of the galaxy here. So one name, so this gas structure is connecting together many famous star-forming regions that we've been studying for decades, if not centuries now. And one of them you might notice here, this is the Orion star-forming region. It sits right at the bottom of this part of the wave here. So if you look this winter at the night sky and you see Orion's belt right here and Betelgeuse, and all these famous bright stars that you can see very famously on the sky, you can know that these stars formed in what was part of this larger scale Radcliffe wave structure. So that's a very giant gas star forming structure in our own galaxy. So I'm going to show this movie now. So if you take the young stars that are along this wave and you look at their motions, and I'll explain this more in a bit, but Gaia also gives us the three-dimensional motions of stars. You can actually find that the Radcliffe wave isn't just by chance this undulating sort of feature. It actually is oscillating like a wave. So this, for example here, this blue clump here, this is Orion, like I was showing before. If you take its motions and you take the motions of the rest of the wave, you can see that they're bobbing up and down exactly the way that you expect a wave to bob up and down in a galaxy. So it is a 10,000 light year long coherent structure that is oscillating in our own galaxy, and we're sitting right next to it. So here it is, again shown on this map here just for reference. So it's a very large structure, and one thing you'll notice here, given its size and given the fact that it's 10,000 light years long, and it's sort of a linear feature, you would, in essence, think that it's part of a spiral arm, or it is tracing a fraction of a spiral arm. And that's exactly what Joao and his colleagues thought when they discovered it, is that this is actually a spiral arm that they're looking at here, this Radcliffe wave, or at least a portion of it. So what is a spiral arm? So first we have to understand that. So here's an animation. And so one thing to know about spiral arms is that they're not material features that are rigid together or going around the galaxy. If you actually trace the particles in this animation here, you can see that these spiral arm features are staying relatively stationary within here. But if you look at any one of these dots here and you follow it, you can see that it passes through the spiral arm and then it later passes out of it. So spiral arms are what we call density waves. They're kind of like traffic jams. So stars orbit along around the galaxy for hundreds of millions of years, and when they encounter a spiral arm, they're encountering this traffic jam, and then eventually they'll pass out of it. So they are these sort of stationary features. Now, what happens to gas when it encounters, or what do we think happens to gas when it encounters a spiral arm? So when stars encounter a spiral arm, not much happens to them. They've already formed as stars, so they don't really care so much. So they just pass through and they exit. But if we consider gas, the things that are going to eventually form stars, what can happen is, so here's this cartoon, this gray thing here is representing the location of the spiral arm. And one thing to remember is that there's more stuff in the spiral arm than there is outside of it. So there's more mass here. So that means there's more gravitational pull. And so what happens then when the gas that I'm showing with these red blobs here, when it encounters one of these spiral arms, is it gets pulled by it, and then there's this increase in the mass density, and the gas, which is very diffuse, feels this huge buildup in pressure, and that causes it to eventually want to collapse and start to form stars. So what we understand spiral arms the role we understand them to play is that they could actually be causing the larger scale star formation patterns that we see in galaxies as these natal these star forming nurseries pass through. Okay, so here's another sort of fun animation or video that shows kind of the scale of the Radcliffe wave. This was a press release video that was created right after its discovery back in 2020. So that's starting on Earth. We're zooming out. Now we're outside of our own solar system. And now we see this cartoon of our own galaxy, kind of similar to the one that I was showing before. And then the Radcliffe wave will be overlaid on this feature, which traces a spiral arm. So none of this was possible. The ability to discover something like this was only possible thanks to Gaia. The increase in data that we achieved from this mission provided a huge boost to getting stellar distances for all of these stars. So this map was totally an unprecedented thing, and this discovery was very huge to see all these famous star forming regions aligned like this. Okay, so now I'm going to get more into dynamics. I'm going to show more of things moving. And there's one special type of catalog that's been produced thanks to Gaia data that helps us track this sort of dynamics. So what I'm showing on the right here are locations in our galaxy of star clusters. So this is a recent Gaia-based star cluster catalog. For each one of these points here is representing a collection of stars. So You might know the Pleiades. This is an example of a star cluster. This is a collection of stars that all were formed in the same molecular cloud complex, the same stellar nursery, and then have traveled together through the galaxy after they formed for millions of years. So again, each one of these points here is not just one star, it's a collection of stars. So the Pleiades here would be represented by one of these points on this map here. And there's something really, really useful about star clusters. And it's the fact that, we can map them in 3D very precisely because they contain multiple stars. So you can average over them and get a more precise distance estimate. And then they also have these 3D velocities. And what's cool about that is that for all of these stars here, you have an arrow, which I'm not showing here, but I'll show kind of in a second, that tells you which way they're moving throughout the galaxy. So you know how the dynamics of these clusters work out. So that means you could play this movie forward and see where they're going to go in the future. But what I think is more interesting is actually you can just flip that arrow backwards and see where they came from. Because we know the ages for each of these clusters, we know how old they are. We have methods to determine how old they are. So you can, not only can you track them backwards, but for the young ones, you can track them backwards and see where the past star forming complexes were, or the past locations of stellar nurseries were. Okay, so we're gonna show that here again. This is our view of the Milky Way here. This is the sun out to the left. And this is gonna be sort of the box that we're focusing on. This is the region where we have good star cluster data where we can do this sort of analysis that I'm talking about. I'll zoom in on it here. So this box is about 6,500 by 6,500 light years across. And now I'm showing these gray points here. Again, each one of these points is representing a collection of stars that were all born together at some past time, sometime in the past. And these are just their locations today. And we just happen to be us on the yellow point here, the sun, or the Earth. We happen to be passing through these star clusters right now. So we have good data of them. So this is to highlight the fact that these points are not just gray boring points. Many of these are very famous star clusters that you can see on the night sky. This one's the Southern Pleiades here. This is Messier 6, also known as the Butterfly Cluster, and this is the Alpha Persei Cluster. So these are all clusters that have been studied for hundreds of years now, that we now have this mapping of and we have the dynamics of. Okay, so now I'm going to play this movie backwards in time. So just to remind you what I'm doing, I'm taking these present day positions of where the clusters are now. I'm taking the way that they're moving and I'm just flipping it backwards to see where they came from. And so I'm going to play this now backwards. Okay, so now I need to make the background artist rendition go away to play this in time. And so now we're going to step backwards in time back to 30 million years ago. And we actually have the precision to be able to trust this sort of analysis. Thanks to Gaia. So here's again the present day. 10 million years ago, this is where the clusters were. It doesn't look so different. 20 million years ago, you start to see some change in the distribution of these points. And then 30 million years ago is where you start to see something really interesting. And you see that now in this picture, compared to the present day, they all seem to go back to one of three compact locations. So these clusters, a better way of putting it is you're kind of like you're starting with sort of like a scrambled egg or like an omelet, and learning that you actually began with 3 eggs. This is what this analysis is kind of teaching you. And so this was work of my thesis that I did here in Vienna, along with many of my wonderful colleagues. What we ended up calling these were star cluster families. So each one of these groupings of clusters that we see when we go back to these previous time steps 30 million years ago are families of clusters that were each born in the same stellar nursery. So each one of these locations here, where it's more compact, is representing times where stars were being born in nurseries. So any one of these regions back then would have probably looked something like this. So a vast gas complex. And so it's really, really amazing that we can trace this thanks to Gaia data 30 million years ago, even further back to 60 to 100 million years ago. And this is just showing their distribution of stars on the sky here. So this is some of the more notable clusters within each of the three families. And then now the points which are distributed on the sky might kind of be a little bit difficult to see, but each point now is showing individual stars of complexes. So you can see the present day location of all these clusters is scattered across the entire sky. So they're all over the place because they've drifted apart from each other, and we're passing right through the middle of all of this. So one thing that's interesting when you go back to this dust map, this gas map that I was showing previously, is when you compare the locations of these young star clusters today to the distribution of the gas, what you find is that the clusters almost always are located within these voids where you see this absence of gas here. And this is indicating that the clusters that are located within inside them, this ellipse here is highlighting a previously known supershell in our galaxy. So that's actually a void where there's very little gas and dust. What this is indicating is that the formation of these clusters had something to do with the formation of this void in the first place. If you remember back to the video that I was showing at the beginning of the presentation, after all the star clusters had formed and all of the violent energy was pushed into the rest of the gas, the cluster at the end was left sort of unobscured in this sort of shell afterwards. So that's what we think is actually happening here. And when you do the math and you calculate the number of stars that should have exploded within this shell, or within this family of clusters, you expect that around 100 supernovae should have actually gone off, and these would have certainly pushed the gas and dust. If you take the distribution of the shell and you ask, given the size of the shell, how many supernovae do you need to get something this size, you need around 100 supernovae to have produced it. So that's further evidence that there's this that this family, this cluster family, is actually responsible for carving out the gas in our local galaxy. Yeah. Yes, this is true. Yeah. So the Radcliffe wave actually is right here. If you got it. Yeah. So the Radcliffe wave, like Orion and all of that, these have formed actually right after it. And it could be, we're not sure yet, but it could be that this explosion and the pushing of the gas could have something to do with the buildup of the Radcliffe wave. That's to be determined yet, but yeah. Okay, so I want to show this family a little bit more in detail here. It's evolution over time. So because it's interesting to look at again in this picture. So here again, what I'm showing here is we're starting at 30 million years ago, where it's this really dense, compact grouping of clusters where there's probably at this time a lot of star formation still going on. And as you go forward in time, I'm making the points turn on when they're forming. When the cluster is forming, you'll see the points there. And then after it's formed, it disappears again. So you'll see at each time step locations of where star formation is happening. So when I go from 30 to 25 to 20, so steps in 5 million years, you can see this pattern of star formation where things have been pushed outwards. So here star formation is happening here, then it expands outwards, and now you get more star formation and outside of it, probably in an expanding shell. And then at the end, you're left with this shell surrounding it again. So the same thing I was showing before. So I'll just play that fast because it's kind of fun to go through it. Okay. And then again, to remind you, we don't have just this top-down picture. If we want, we can turn this on its side, view it from any angle. So we have access to basically a galactic supershell and the star clusters that formed it in full 3D across time. So the Milky Way is really the only place that you can do this sort of analysis, at least the region within 10,000 light years. Now, again, this image that we got from JWST of this galaxy where you see the spiral arms, you also see similar bubbles. And this here is called the phantom bubble. This was a discovery that was published a couple of years ago. And so what they found also is when you look at this bubble, I'm zooming in on it here, and then the colors are a bit less exciting. But you can see sort of the same feature here with a void in the middle here. When you look at this bubble and you then switch to different wavelengths of light, you look at the optical from the Hubble Space Telescope, you can see young clusters within it. So you have the same sort of picture where supernova and this sort of violent energy momentum feedback that the massive stars gave off have pushed and formed this shell. And so to overlay to similar scales what we're seeing in the Milky Way to what you see in external galaxies, they're very similar scales here. So this is the same family with the supershell overlaid on top of it. And again, so the external galaxies, you can see all these different voids and you have this very large scale picture of it. But in our own Milky Way, maybe we have one very large supershell, but we have a full 3D time resolved picture of it, which is something that's really, really useful to have when studying these sort of physics. And then I want to focus now on one of the other families really quick here. This is what we call the Alpha Persei family. This includes a lot of really famous young star clusters that, again, you can see on the night sky. So it begins, this is a timeline here, it begins forming around 60 million years ago. This is 60 million years ago now, with a few clusters here, 4 clusters forming. And you step forward in time, 60 to 45 to 30. And again, you can see the stars pop up as you go forward in time, and you have these very famous clusters that I won't get into too much here forming. So it's kind of a similar picture as the last cluster family. The reason I wanted to highlight this family is that this cluster family produced perhaps a more famous bubble. This is called the local bubble here. So it's not as large as the other supershell that I was forming, but it's the bubble that we happen to just sit right in the center of, hence why it's called the local bubble. And so what's been found recently is that when you look at the local bubble and you look at where star formation is currently happening, all star formation that's very close to the sun is situated on the edge of these local bubble of the local bubble. So again, similar picture, you have supernova going off, explosions going off within this cluster family over time, and they form these bubbles. One of the latest to form is the one that we happen to pass through, where we have this very detailed, when you zoom in, picture of star formation here. So here is highlighting some of the star forming regions that currently sit on this bubble. This is Taurus here, very well studied region. And then this is Corona Australis, that is one of the star forming regions that's being highlighted here. This image actually is taken from a survey that's being conducted here in the same group by Stefan Meingast. So this is a Vienna-based survey of star formation happening on the surface of the local bubble here. So this, I've left my summary slide here in just one sentence, but the main takeaway is that before we had this wonderful data from Gaia, we really didn't have a clear view of what the galaxy around us looked like. We could only kind of make guesses based off of other data sets, and we didn't have this picture of these really precise distances showing us spiral arms. And on top of that, now with Gaia, we have the ability to trace star clusters backwards in time, and not only study star formation today, but also study where star formation happened in the past. So this has been amazing science that's come out from Gaia over the past few years, and there's many more to come. So Gaia is no longer operating. It shut down actually earlier this year, but there's still at least two data releases to come over the next 5 years. So the data will continue to improve, and this picture that we have of our galaxy will continue to get better. So I'll play this video here, and then I'll be happy to take questions. So thank you. Question? Maybe I shouldn't have played this video during question time. No.
Well, thanks for this great talk. If you do have questions, please wait for the microphone for the benefit of our viewers in South America. We have them.
Early on in the presentation, you were talking about young star clusters and young star formations. And you mentioned that some suns were potentially exploding quite early on in the birth of this young cluster. I just wondered if that was just a normal, like the normal star life, or do young stars fail and explode early?
Great question. So it's not the normal star life. So most stars get to live for a long time, like our sun. But in any massive star forming region, there will be at least a few very massive stars that are greater than 8 times the mass of our own sun. And when you go past this limit, the star has a hard time producing enough energy to keep it sort of pressing outwards to counter gravity. And so what happens then is these stars only live for a very short period of time, and then they collapse and explode and go supernova. So most stars are easily surviving their past star formation for a very long time, but the very massive ones die quite relatively quickly, within a few million years or few tens of millions of years. Yeah.
Other questions? Yes.
So it looks like the sun is a little bit separate from the other star clusters. Why is that the case? Is it a special case?
Yeah. So the timescales that I'm showing for this cluster movie is tracing the past 60 million years, and the sun forms much longer ago, billions of years ago. So the sun has gone around the galaxy many times, and we just happen to be passing within this region where young star formation is happening. So there's a huge time difference between these young star clusters and the stars that are forming. These are millions of years old, so very, very, very young. Sun is an old star, so that's why there's no connection between the sun and these star clusters.
It's just a coincidence that we are looking now at the ones that are early and okay.
Yeah.
Thank you.
Yeah. But question?
Yep. One more question. There was sometimes there's gas mentioned, and sometimes there's dust mentioned. And which gases are creating these nebulas, and what's the difference between the gas and the dust?
Great question. That's actually kind of a hard question to answer, but I'm using gas and dust sort of interchangeably. On these large scales, the dust, they're basically grains of like silicate and stuff that's just kind of floating in space. These things trace the gas quite well. In star forming regions, what we're typically looking at is hydrogen, so neutral hydrogen. And what happens in star forming regions when it gets a lot denser and a lot cooler, this neutral hydrogen, atomic hydrogen we call it, pairs up with another hydrogen particle, and we call that molecular hydrogen. So that's where the term molecular cloud comes from. These are regions where there's high density, so you can get this molecular hydrogen, and then that goes into the formation of a star.
So a more general question, which is probably not completely related to that, but so the formation of galaxy and of structures. The universe is a complete symmetric system. So why is the galaxy always in a what determines the direction of the spiral rings and the it's flat in the end. So why is it flat in a certain direction? What defines that?
I have no idea. So that, oh gosh, yeah, you're really probing outside of my level of expertise. But yeah, so as I was mentioning before, the universe has gas in it. And then at the larger scales, gravity is what's controlling the structure that you see. So gravity is taking over the gas and creating all these cosmic filaments, which at the hubs host galaxies. And then there's a bunch of complicated physics that I could get into as to why it actually is a flat disk, like something like angular momentum. But I don't know if rotation. Yeah.
Yeah, it's rotation, but the question is, of course, everything is completely symmetric at the beginning. So it's starting in a single point. That means everything is symmetric. So what is determining the exact plane? So that is this plane and not that plane, for example. Random. Thank you.
Were there any challenges in tracing back the movement over these multiple clusters over these long timescales?
Great question. So the number one thing that limits us to tracing these back before Gaia was the fact that first of all, we didn't have very precise distances to these star clusters, so we didn't actually know where they were in the first place. And likewise, we didn't know how they were moving. So if you have very fuzzy information with this type of, in terms of star clusters, and you can never figure out where they were millions of years ago. So that's what Gaia has done, is it's provided extremely precise data that's leaps better than what we had before and allows us to trace it backwards in time. There are other limitations to this too. So if you trace a cluster backwards in time, you are assuming some things about the properties of the galaxy that you want to get right. So probably we couldn't take these clusters and trace them back like 500 million years for sure. We couldn't do that. It's going too far backwards in time. But within 100 million years, we think this is fairly safe for this type of analysis.
Right. Then, thanks again, Cameron.
Thank you.
For the best for your future. Cameron is fortunately leaving us, returning to the US.
Oh, somebody asked, is there a successor for Gaia? Yes, there's a planned successor. It's called Gaia Near Infrared, and this would basically, so Gaia is an optical telescope. It sees in wavelengths that mostly we can perceive. But Gaia has a hard time looking at stars that are presently located within the very dense molecular clouds, like the one that I was showing before. So Gaia Near Infrared would potentially be able to see through this, but if it does launch it, I'll already be old by this time, like probably in decades.
He's too old. Right. In the nearer future, the next talk will be actually more of a musical session, as far as I understand. There will be a general talk about astronomy as science and inspiration for music, and there will be music, a harpist and a singer. Therefore, I'm not very clear about the plans. I guess it will be interesting. Even closer, if you wish, you can join us to the telescope. Now we meet just outside the lecture room and around the Meridian Circle. Then, thanks again.